To answer this question without an argument of which boat gets to the other shore the fastest, or we could also say travels the shortest distance, right? Which one will get there the quickest or travels the least furthest, knowing that the current is flowing downwards at some speed. So you notice on each boat here we have the vector showing the current pulling each boat, right? And then you got this other vector showing the direction that the boat's taking off. So in combination to the boat's vector and the river's vector, where does this boat end up? Okay, so to answer that question, we have to learn a rule in physics called the parallelogram rule. So I'm going to use some jets here to answer that boat question. If what this rule says is that this jet, if you were to fly this direction, it's the same thing as if this jet flew in some different direction and then a second path. Let's say the jet takes off in this direction for a while and then turns and takes off in this direction and ends up in the same place. The parallelogram rule says this, that it doesn't matter if the jet first, takes off in this direction, in this vector and then turns, or he could have started in this direction, right, and then turned and then went in this vector's direction and ended up in the same place. So that's what's known as the parallelogram rule, that you can, when you add two vectors, two directions, it gets you to an ending place. It's what we call the resultant vector. So a good example of showing you that if you take two different directions, it doesn't matter what order that you do them in, because you'll end up in the same place. This is what's called the parallelogram rule. So let's take a look at this boat problem again, because really it's the same thing. You've got the vector, showing the the speed of the river and the direction that the river is flowing, and then you got the vector showing the direction that the boat's going. So to figure out where this boat's going to end up, we can add our vectors. So we could actually take this vector and put it on the end of this vector, right? So I'm going to use my vector from point. You're going to hear the word vector about 200 more times, I think. So I'm going to click on this point E to start my vector, and then I'm going to click on this vector here to add it. And now, if you think about it, it's the same exact rule, that if the boat takes off in this direction but is affected by the river in this direction, together the boat's going to end up right here, right? It doesn't matter if you add the boat's direction to the current vector here, you end up in the same place, right? So let's see where this one ends up. So if I put a vector in the boat's direction, one in for the current. So now I'm going to use my vector from point tool. I'm going to click on this point and I'm going to add this vector. So that means that the boat really ended up right here. Okay, and then the last one, we've got the river's current again, and we've got the boat's direction. So now, vector from point, I'm going to add this vector on. Notice this one kind of seems like it traveled the furthest, right? It traveled right to that point. So if we use our distance tool real quick, we could check to see this one traveled the length of, let me put a segment on these. So the fastest, if they're going the same speed, sorry, that's a point that I probably should have mentioned at the beginning of this. These boats are traveling at the same speed. We can see which direction made the shortest distance, which implies that the boat got there quicker, right? Got there faster if you have to travel less of a distance to go. So you can see here that A, heading into the current, knowing that the current's going to pull you down this far. If you head into it, you're going to travel the furthest distance, which is really perpendicular to shore. I'm just going to put a line on shore here. So notice that distance is pretty perpendicular. If we were to actually continue, or even do a line here, not quite 90, would be if we went maybe there. That'd be the shortest. So anyways, the parallelogram rule kind of can answer that river question just by comparing two different motions. Good physics question. So now your job is to mathematically prove that this is always true, right? If this is a rule in physics, it's something that has to be proven to be true. So we're going to prove that this is always a parallelogram. So basically, if you take that jet problem again, or the boat problem, doesn't matter. For what we want to prove here is that this is truly a parallelogram, that if the jet traveled this distance and then turned and went in this direction, it'd be the same as if you reverse that order, right? That's what we're going to prove here. So we're going to try to show that this is a parallelogram. And to do that, we're going to prove that we have a pair of parallel sides. And we're going to talk about how we're going to argue that, okay? So first of all, here's what your proof is going to look like here. So we have just some parallelogram that's going to represent all parallelograms because it's just a generic picture, right? And we have labels. I labeled it jets. Okay, so we're going to prove that jets is a parallelogram. And so just like in the parallelogram rule situation with the jet and also with the boat, we know the distance, we're going to take this direction and length and then add to it, let's say the jet takes off in this direction and then turns, or we switch those vectors, those directions, right? So what we're going to assume then in this, what we're going to be given in the problem, is the fact that Sj is going to be congruent to Et, and then also this side is going to be congruent to this side, because if there are motions, right, jet either flies here and then turns, or flies the second direction first and then turns, ends up in the same spot, right? We have the same resultant vector either way. So to prove that this is a parallelogram, this is what we have to do, okay? So make sure that you have this written down. You either can, what I would recommend is on a sheet of paper, just write this down here. You're given, here's your given statements, which is just what I showed here visually. And then your prove statement, prove that it's a parallelogram. And then have some notes here. So this is probably something I should have done earlier, and I apologize. But now that we are talking right now, let's take a look at this here. So the first thing, this is what I was thinking about. Well, what would I do first or think about first? When you start your proof in the body, you always start with your given information. That's really your starting point of your argument. So you're writing your argument down in your proof. That's what the proof really is. So as it flows downward, you're just connecting statements that are true, that have to be true. Okay? So the second thing you're going to do, so first thing you write your givens, that's our starting point for our argument. So the second thing you need to do is you're going to show that this is a parallelogram, we need to show that both sides are parallel to each other by forming an argument that there's an angle pair that forces parallel, right? Like there's an alternate interior congruence in angles, there's a corresponding angles, or an alternate exterior, and show that those angles are congruent and that they have to be, right? So if we have some in here, for example, the way this picture looks, the way this diagonal or this vector is drawn, what it's doing right now is we can argue that if these two triangles are congruent to each other, right, that's the next thing that we have to think about. These angle pairs that we're going to argue are congruent to each other, like trying to force or show that one of these angle pairs are congruent and existing. What we have to think about is these angles, they're just corresponding parts of a triangle, right? They're just angles or sides. That's all that a triangle is. So what we're trying to show is that these angle pairs, maybe alternate interior angles, for example, in this picture up here, right? If we could show that, say, this angle is congruent to this angle, then we know that these lines have to be parallel, right? That's just, it's a property of geometry. Or we could show that this angle right here is congruent to this angle here, and in that case, these sides have to be parallel, right? And therefore, this is a parallelogram. Okay, so to do that, you first start with your given information. We're given that these sides are congruent to each other, because that's going to allow us to then think about, after we think about these angle pairs, right, these alternate interior, for example, that can argue that these sides are parallel to each other, we have to think that they're just corresponding parts of two triangles here that are congruent, right? So our argument has to start by taking what we know from the given and using that plus extra facts in the picture, right? If they share something, or some kind of property that we know has to be true, we can state that in our proof, right? So that we can build some kind of triangle congruence. So that's the next part here. So if you prove the two triangles in the diagram are congruent to each other, you have to be arguing that there's a triangle congruence combination, right? Like side, side, side. All three sides have to be congruent to each other. Maybe you have two sides congruent to each other and the angle between them is congruent in both triangles. Then you have congruence. Angle, angle, side, angle, or HL theorem if you have right triangles. You have to prove that they exist, and therefore the triangles are congruent and all six corresponding parts are therefore congruent. So then you can state, now that we've argued that we have some congruent sides and angles and whatnot that makes the two triangles congruent, then we can go ahead and say, well, okay, if they're congruent to each other, then their corresponding parts have to be congruent. So there's sides that are congruent to other sides. We can say that without a doubt. There's angles now congruent to other angles, right? Just corresponding angles in the two triangles, right? It's just arguing equal parts in equal measure. Okay, so what I would do again when you're going to write this formula, you start with your given information. You're going to first prove that these two triangles, like triangle JES and triangle TSE, right, are congruent to each other. To do that, you're going to prove some kind of triangle congruency combination, and you're going to just argue then that if they're congruent to each other, then some corresponding angles, like these alternate interior angles, they have to be congruent to each other because they correspond to each other in congruent triangles, so they have to be congruent. And therefore, if those angles are congruent to each other, you have parallel, because that's how we argue parallel. Okay? So think about that as you try to prove that this is a parallelogram.